And hello, welcome everyone to this video. So it's been a while since I last posted. I've been doing some work behind the scenes. I was like saying, yeah, this is a little bit of a headache trying to differentiate this Churchill correlation. And just a note, I think my Churchill correlation is kind of wrong in the last video. My A and B specifically is kind of wrong. This is the correct Churchill relation. Of course, for this one, there's a Moody friction factor. It's kind of calibrated for the Darcy or Moody friction factor. There's a factor of 8 in front rather than a factor of 2 in front for the fanning friction factor. So you can see that there's a factor of 4 difference between both of them. Okay. And then I think my A and B, I'm missing a power for the A, and the way I typed out the A was kind of wrong. So let's just yeah, I see. Where is it? Yeah. Okay. Never mind. I'll just go to the code, VS Code here, and I start from here. Okay. And then let me remember there's a key for this. Oh, hold on. There's always a key to sync properly. Alt-J. Okay. Let me. All right. So as always, Stack Overflow comes to the rescue. So this is the answer given by I think, is it Jojo? I think so. Yeah. Answer given by Jojo. What you're supposed to do if you want to use the command to jump to the specific line of code is to use ctrl-alt-J. So let me look for the Churchill. Okay, ctrl-alt-J, that will bring you straight to here. Okay, so as you can see, alright, I think I made my correction over here. There should be a power 16 in front of the A. Over here, there should be 7 over Reynold's number, not 1 over 7 over Reynold's number. So this is what the equation should look like. So that is the correct equation. Okay, let's bring it to the correct equation. And then of course I will just correct it in front of you. So instead of, yeah, I'll just delete this fraction. I'm using the Vim key bindings here, so it's good. I'll delete this extra curly brace and that should be fine. Ctrl-alt-J. Yeah, and this is what the thing should look like. I think I want to make the thing a little bit more a little nicer. Replace it with curly, replace with curly, and I'll replace this with a curly. Now insert another curly here. Okay. Okay. This should work around about right. And there you go. One more bracket. Kill that other bracket. Okay. Yes. As you can see, this is the correct formula right here. Okay, this is the correct formula right here. So yes, the last time I told you I was not very keen on yeah, I wasn't very keen on differentiating this. Now I was telling the truth. It's not a nice thing to differentiate, but I did differentiate the thing by hand. I hope I got it right, and there must be ways to explore whether it's right. So I'm gonna walk you through the strategy and some of the code that I've already implemented. Okay, so let's go to fluidPipeTheory. I made a fluidPipeTheory markdown file. A fluidPipeTheory markdown file, which I can also preview. Yeah, markdown is much nicer to preview. Okay, so this is just some introduction and some traditional SpiceSharp calculations. And here is me. Here I am trying to justify how can I just replace the charge with either a volumetric flow rate or a mass flow rate. Okay, at the end of the day, I chose to change it to mass flow rate because current is always conserved. Okay, so I'm changing voltage, I'm changing current into a mass flow rate per unit time. Okay, so I'm changing everywhere the charge appears, I change it to mass. Okay, so it's how much mass per unit time, how much energy per unit mass. So I'm using a kinematic pressure rather than what do you call that, dynamic pressure drop. Why is that the case? Because in this case, Kirchhoff's current law, it talks about the conservation of charge. No matter what the density, how the density changes, okay, talks about conservation of charge. Now let's say there are some parts of the circuit, the flow circuit, where the fluid density changes even a little bit. Okay, the conservation of mass will hold, but the conservation of volume, okay, conservation of volume will not hold because now the fluid is compressible. So that you cannot apply that law. If not, it will result in some kind of calculation error. So while kinematic pressure is a little less intuitive to work with, I've opted to work with that because it makes sense for the code. It makes sense physically to translate from Kirchhoff's first law or Kirchhoff's current law. I translate it into the conservation of mass. Okay, so here are our pipe equations. Hopefully this time I typed it out right, but again you can see I didn't type it out right here. I need to change that again to 7 over Reynolds number. So okay, 7 over the Reynolds number. Let me get rid of this bracket and put it here. Okay, nice thing about Markdown is that your preview updates instantly and you don't have to press Control Shift J or Ctrl-alt-J just to quickly get your code in sync like you have to for LaTeX. Okay, for LaTeX you will need to keep pressing save and then Ctrl-alt-J to bring you to the preview. Okay, for Markdown you don't need to. So I've been using Markdown a lot to document the code. It's readable on GitHub, so that's why I kind of forgot my key bindings for a little while. Alright, so here are our pipe equations. We use the Churchill correlation here to calculate the fanning friction factor. Okay, so just to make sure, okay, just to make sure we are doing Fanning's friction factor. Let me just put Fanning friction factor thing here so that there is less ambiguity. Alright, and then I will just say for short, every time I use F, it refers to fanning unless otherwise stated. Okay, of course I can do something else. I might update the code later, I might update the documentation later, but I don't want to do it now. Okay, may update documentation later to always use subscripts. Okay, so this is what we have here. Alright, so the fanning friction factor is equals to this Churchill correlation, and this friction factor, when you put it in the context of pressure drop, how much pressure drop there is, okay, the friction factor actually correlates delta P over 4L over D half rho U squared. So if you take a look at fanning friction factor, okay, where do we get the formula? Okay, here it is. Okay, Fanning friction factor, named after John Thomas Fanning, is a dimensionless number, blah blah blah. It is defined as the ratio between local shear stress and the local flow energy, respectively. Okay, so yeah, I think yeah, that's why okay, if you can see here, Okay, delta P over 4L over D. I believe this is some representation of, yeah, local shear stress. Delta P over 4L over D. Okay, and you have the half rho u square term right here. Okay, so okay, so anyway, where did I get the formula from? Okay, you can see delta P equals to the friction factor times L over D half rho V squared. Okay, this is using Darcy's friction factor. Okay, Darcy's friction factor. So if you want to substitute it for Fanning's friction factor, okay, let me put the source here. Okay. Yeah. So the source is, I'll need to, oh yeah, I need to put this source for Darcy friction factor equation. Now I'll just put this here, paste the link. Okay, pressure loss in pipe, and I'll open up a new line. F, okay, F Darcy equals to 4 F Fanning. Okay, that's how you get it. And then the Darcy friction fact, okay, the pressure drop here is correlated like so. Okay, the pressure drop is correlated like so. The delta big P small p, I mean this is dynamic pressure. Okay, delta P equals to what? F Darcy. Okay, F Darcy times L over D. F Darcy times fraction L over D. And then what's next? Half rho V squared. Fraction half rho U squared. Okay, half rho U squared. So this is, if you want to just substitute in, and then we will get this equation here. This is just to derive, just to make sure that there's no careless mistake or anything like that. Want to be very careful. Okay, paste it here. I'm using all the Vim key bindings, so that's how I'm doing all this. Okay, so this is what we have, and then I'll yank and paste this. I'll put this 4L over D here. See, I just shifted the 4 in, and this is how we get the expression for Fanning's friction factor as an expression of pressure drop. Okay, so F Fanning. Okay, so F Fanning right here. Oh, okay, back N A. Alright. Yeah, Vim still takes a while to get used to, but yeah, it's good to use. Very ergonomic. Okay. Oops. Shucks. Scrolled down too far. Alright, so as you can see, there's a lot of content to cover. So pardon me for going, I don't want to make too many mistakes here, so pardon me for going slow. Okay. So yeah, let's check out. Right, so what are we doing here? Okay, this is the Fanning friction factor. From the Darcy equation, we will get this sort of equation here. Let me do some manipulation to make the Fanning friction factor the subject. Alright, and then we find that delta P equals to F Fanning times 4L over D half rho U squared. So this is what it is here. Now if you want to substitute the fanning friction factor and everything in for this, then this is what it will look like. Alright, so where are we now? Not 4L over D. Yeah, I need to take out the F fanning. Visually take it out. Yes, now this is the correct equation right here, an equation for pressure drop. Okay, now again here we have our A, B and Reynolds number. Okay, Reynolds number, I don't really want to always put it in terms of U. I rather put it in terms of mass flow rate. Why? Because mass flow rate is something you can kind of do independent of pipe, independent of flow profile. Okay, whereas this velocity here has to be some fluid average velocity, whereas mass flow rate, yeah, you don't have to make assumptions about what this velocity is. You kind of just know. Okay, but of course this is the mass average fluid velocity. This is B. This is B. Okay, and this is A, this time with the correct equations. Alright, and this is the Reynolds number in terms of mass flow rate. Okay, so the next part describes how we can change the current balance to pipe mass balance. Okay, so these are some of the equations. I'm going to skip through most of these things. Alright, I have an image pasted here. Alright, actually maybe I won't skip. I'll just talk through them briefly as fast as I can. How do we relate the current and voltage across a resistor? We use Ohm's law like so. Okay, if we were to substitute the voltage for kinematic pressure the way we saw before, okay, so voltage at A becomes kinematic pressure at A. Now I have not included height or anything down here, or hint, so this is kind of incomplete still. Okay, so this kinematic pressure kind of called, you have to include and throw in the elevation there somehow. Okay, the pressure at A minus pressure at B, the kinematic pressure at A, pressure at B, of course I put the units there so that there's no confusion, equals to the mass flow rate, or divided by the flow resistance is somehow the mass flow rate of the pipe. Okay, so unfortunately the relationship isn't that simple as we discussed before. Okay, except in a laminar flow regime. Okay, laminar flow regime is it's a bit different. You can almost use Ohm's law if I'm not wrong for laminar flow regime. For any other regime, you can't really do that. Okay, so for laminar flow regime, friction factor is 16 over Reynolds number. Okay, so let's check out the laminar regime. Ohm's law is actually obeyed in a laminar flow regime. So this is the friction factor, fanning friction factor is equals to the absolute dynamic pressure drop divided by 4L over D half rho U squared. Okay, in laminar flow regime, the fanning friction factor is 16 over Reynolds number, so this is what we substitute in here. And Reynolds number again in terms of mass flow rate is mass flow rate times diameter over, or the hydraulic diameter divided by mu times A cross-sectional area. Okay, so and of course the more classic way is rho ud over mu or ud over nu, which is a kinematic viscosity. So I'm going through this very quickly. Alright, so I substitute in the Reynolds number there, the rho ud over mu here. Okay, and I do some term cancellation. I bring the 4L over D up, I multiply into the 64. Okay, I cancel the u's on both sides. Okay, I cancel the u on both sides, and then I have a rho d square. I bring the d right here. I bring the d right here. Yeah, I bring the L over D over here, and I put the L on top, D at the bottom. So it's rho d squared at the bottom equals to, okay, 64 mu L over rho d squared equals to delta P over half U. Okay, of course I can bring the half over to the other side, and I substitute mass flow rate equals to blah blah blah. So okay, I think I should state properly. Okay, velocity equals to mass flow rate over density times cross-sectional area. I substitute that in here, and I put the delta P over mass flow rate as this ratio. So I bring the half the mass, the density and the cross-sectional area, I bring it all over to the left-hand side. Okay, I multiply the half into the 64. I put the cross-sectional area, everything, all this stuff at the bottom, and then you can see that this thing over here, for constant fluid properties, for mu equals constant, pipe cross-section, pipe dimension is constant, the kinematic, or rather this dynamic viscosity, oh, not dynamic viscosity, what am I talking about? This is the density. Okay, for density constant, everything constant. Okay, all your terms on the left are pretty much constant for constant fluid properties and constant pipe dimension. So in that case, Ohm's law is obeyed. Okay, for laminar flow, Ohm's law is essentially obeyed, and there is an explicit relationship between this pressure drop and kinematic pressure drop and mass flow rate. So this is very good. Okay, unfortunately, most of the times the Ohm's law will not be obeyed. As you can see, if we take a look at the Moody diagram, which I conveniently copied and pasted from this nuclearpower.com WP content blah blah blah, I copied it from this website, and I use this thing to paste the image in here. Okay, and of course I will cite. See, I have citations here, so of course you need to cite. I do need to cite, and that's always good practice. Don't want to plagiarize or anything, but yes, this is where I got that image from. Okay, so I retrieved it from there. Actually, in terms of any engineering handbook, you should be able to find one of these there. Okay, from Paris as well or whatever. Okay, so of course, if there are copyrights problems, I'll probably just take it down, but shouldn't be an issue at the moment. Okay. Okay, so and yeah, it's educational anyway, so you should be able to use this. Right, so this is Moody's diagram. You can see that on the right hand side we have turbulent flow. This law isn't obeyed. You don't have the friction factor. I mean, you don't have this Ohm's law being obeyed. Okay, so this is just some more derivations for you. Okay, you can see all the way on the right hand side, after a certain Reynolds number, after this transition region, after you reach this part called complete turbulence, the friction factor doesn't really change that much anymore. Now this is very similar to the case not just for the friction factor after a certain Reynolds number. For valves, for bends, all these tend to use the K formula rather than some complicated friction factor formula. Okay, for such a regime, you have your pressure drop over your what do you call that? Half U square. Of course, I absorb the rho into the pressure drop on top, so it's a kinematic pressure drop. Okay. Yeah, just like I did here, I took out the rho from the half rho U square, I put it in here. Yeah, so the kinematic pressure drop is here. You have K at the bottom, and then you just make, if I make U the subject or mass flow rate the subject, this is what we will get. Okay. So this is still okay because we have mass balances. Mass balances are there. The main point of us trying to get all these equations out is so that we can take a look at this. We look at this, and then we need to do some differentiation, right? Okay, so the idea of rewriting all of this out is so that we can calculate the Jacobian over every node. Okay, the Jacobian at every node. So that's what we discussed the last time, where kind of got into a bit of a headache and then said we need to differentiate things. So I'm starting to do that already. Okay, so this is how we can calculate the Jacobian manually. And there are some mistakes in what I did, but yeah, how can we calculate the Jacobian manually? Okay, how can we calculate the Jacobian manually? So, alright, so most of the flow regimes will be inside here before complete turbulence. These are most of the regimes here are the ones causing the problem. Alright, you don't have it's not easy to differentiate mass flow rate with respect to, let's say, delta P. If you have something like this Churchill, okay, let me go up, back up. Yeah, if you have this Churchill correlation here, it is not that easy to differentiate. Yeah, it's not that easy to differentiate this correlation, and not easy to have an explicit delta P with respect to Reynolds number, or with, yeah, it's just not easy to have, sorry, not delta P, it's not easy to differentiate mass flow rate with respect to all these terms on the right hand side. The only thing that's explicit here is that the pressure drop is explicitly related to all these terms on the right hand side. Okay, and then of course you have the velocity here, which you can sort of correlate with the Reynolds number somehow. Yeah, so all of that is dependent on the Reynolds number. Okay, and just for example, how this non-explicit non-linear regime. Yeah, so we are trying to do our Jacobian right here, and this is the reference of how this the non-linear resistor. In the non-linear resistor, we have some example code of how the Jacobian inputs are being put in. Okay, that is something you can go and take a look in your own time. Okay, so this is where you'll find it. iBiasing behavior.load. All the Jacobians are put in here. Alright, so this is the part I'm highlighting, very important. This is the part I'm highlighting. So this is the current, and this is where the Jacobians, I think G, you see Y matrix, they all use this G term. So this G is where the Jacobian is being calculated for us. So very important to pay attention to that part. Okay, so this is the Jacobian, it's being calculated explicitly. Okay, so there are a few options we can go. We can either use a numerical differentiation method to help us approximate the Jacobian term, or we can calculate by hand. Okay, neither of them is easy because let's say you calculate the Jacobian of the using a numerical method. Okay, so that's the easier of the options, but then how do you verify that you are on the right track? How do you verify that you haven't made any careless mistakes? So that is going to be somewhat challenging in itself. Okay, so it is better, of course, that we can write out the derivations out analytically, and we test both the analytical methods and compare it to a numerical method and see whether these methods generate the same Jacobian. If they do, at least you have, if the analytical method and the numerical method match, okay, if the Jacobians match, then at least you can be quite sure that the way we do Jacobians numerically and analytically, that's more or less correct. Okay, so you need to measure those gradients very carefully. Now the tricky part is how do you obtain the Jacobians? Okay, delta FA, delta VA, delta FA, delta VB, so on and so forth. Okay, I'm going to try replacing all of this with the how do you say? I'm going to try replacing all of this with mass, and we remember that all of these terms here, they are not the full Jacobian. They are merely the contribution of the resistor, the current flowing through the resistor. Okay, the contribution. Okay, this resistor right here has nodes A and B. Okay, and it looks like A is the inlet, B is the outlet. Okay, so what we are doing with nodal analysis is to perform a current balance over node A and node B for this resistor. Okay, we are doing current balance over node A and node B. Okay, and what does Kirchhoff's law say? Kirchhoff's law says that the current flowing in and out of node A, okay, when they sum them together, they must be 0. The current flowing in and out of node B, when you sum them together, it must be 0. That is essentially what this F here is. Okay, when you see FA here, FA is actually the current balance over node A. FB is the current balance over node B. Okay, and so FA is actually when you sum up the currents flowing in and out of FA. When you sum all those variables up, you have this F. Okay, so this F is actually the sum of all the currents. Okay, so what are we trying to do here when we calculate the Jacobian? We are trying to find out what is the effect changing VA. What's the effect changing the voltage at A? What's the effect of the current balance when we change the voltage at A due to this particular resistor? Okay, we are only looking at one resistor here and its contribution to the current balance here. All right, so yeah, what is the contribution? To calculate the Jacobian, we need to look at FA and how FA changes with respect to VA just for this resistor in question. All other resistors, every other component, we don't care. We're just looking at this one resistor. Same for VB, and we also take a look at the current balance over the outlet node. Okay, so there are only two nodes and the voltage or the pressure in this case at these two nodes that we need to consider. Okay, so what are the contributions by this nonlinear resistor to the Jacobian? So this is the part of understanding how the nonlinear resistor Jacobians work. Once we understand that, we can then so-called take a look at the what do you call that? We can so-called take a look at translating it to the pipe. So here, okay, I think I'll just stop here because it's already 30 minutes. I don't want to keep going on and on. Okay, but the current this is how we actually calculate del FA del VA for this particular resistor. It's right here, del IR over del VA, del IR over del VB, and so on and so forth. Okay, and then we'll try to convert those into partial derivatives for our pipe. Okay, once we do that, we'll try to figure out how to find these partial derivatives. Okay, so I'll stop now. I'll see you next time. Hope this was helpful in understanding my thought process on how I developed the code. See you.